you happened to be at my talk yesterday, it was a very concrete talk about numbers. Today it'll be a very concrete talk about shapes. And I think it'll be even more concrete. It's a style that I call horsies and doggies style, meaning extremely elementary. Well, not so elementary in the sense, I mean, some of the ideas are somewhat subtle, but what I mean is it's very visual, and I think that even for those people who are not mathematical, it ought to be fun for two reasons. One is because I have some stuff that's in words you'll see that amusing, and the other is that I have lots of nice pictures and animated things, and I think it'll be attractive for that reason. Now, I became fascinated by geometry rather late in life. I never took geometry in high school. Nor at college. I was a math major in college, and geometry was really out of fashion. I mean, nobody ever took geometry in college. They didn't even, at Stanford, they didn't even have any courses in geometry. And I suspect that may be true today also, that it's really kind of not a very trendy thing. But I got fascinated by it back in about 1992. And it rapidly became a passion, and it started out with just an idle question that I proposed to myself that I sort of had heard. It was a puzzle. I'd heard a theorem, and I tried to prove it, and I tried to prove this theorem algebraically. If you want to know what the theorem is, it's a theorem that says, I'm not going to define the terms, just so that those people who know these things will know what I'm talking about, that the circles invert to circles, if you know what inversion is in geometry. And so I tackled this problem in a rather stupid way. I used algebra, and I failed in proving it because I made a mistaken assumption, and so I felt stupid, and finally I corrected. I found, after a long period of time, I found my error. I redid the algebra, and with the correct assumption, and I was able to prove the theorem, and I felt good about it. And then I mentioned it to one of my graduate students who was very good in mathematics, and he said, oh, he could prove it in a very nice way, and he showed me a proof which was entirely geometrical. And it made me feel ashamed of myself, because I had not even considered the idea of proving something in geometry using geometry. It was a weird thing. It really caught me off guard. And, but it was a lovely thing, and so I want to show you not how he proved that particular theorem, but I just want to show you one ingredient in the proof that he used, which was a theorem that, as I say, since I had never taken geometry, I didn't even know. And this is really funny. Oh, let's see, this is a little bit too, come on. Oh, this is not reducing. Why is it not reducing in size? I thought it would reduce in size if I told it to. It's not being very obedient. All right, well, maybe I will be able to get along without that in some fashion, I hope. All right, so I called it the chord angle theorem, and on my screen, for some reason, everything looks, the circle doesn't look circular. How does it look to you? It looks elliptical to me. Oh, well, hopefully on your screen it looks good. So, so the chord angle theorem is a very simple idea, but it's a beautiful idea, which says that that angle at A stays the same as I move it around. And this was a beautiful fact, a fact about circles that I had not known. How could I not know this fact? But I didn't. So I guess I should try to to just give you a quick proof of this. I'm not going to do much proving, but I'll do a little bit of proving. So here's a circle, and here's a chord. Can you see this? Okay. And so I'll draw this line and this line. And here's the center of the circle. And I'll connect these vertices like that. And I'll give names to the angles. So I'll call this alpha. Both of these alpha. Sorry, I can't call both of those alpha. Let me first make a point. These are radii of the circle, so they have the same length. So I can indicate that they're all the same length in that way. Now I have an isosceles triangle. So I will call this alpha, and then this must be alpha because it's an isosceles triangle. Okay, I'll call this beta, and again I have an isosceles triangle, so this would be beta. And then a third one here, this is gamma. And this is also gamma because this is an isosceles triangle. Okay, now if I'm going to move this point around, zoop, 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 obviously some things are going to change. But one thing that isn't going to change is gamma. Gamma is fixed. All right, so I move along. The sum of all of these angles is 2 alphas, 2 betas, and 2 gammas. So the sum of alpha, 2 alpha, plus beta plus gamma is the sum of all the angles in a triangle, which is 180. All right. So alpha plus beta, and gamma is a constant. So 2 times alpha plus beta is a constant. In other words, I can just move the gamma over onto this side because this is a constant and the gamma is a constant. So I get 2 times alpha plus beta is a constant. So alpha plus beta is a constant. And alpha plus beta is this angle. So there we are. I mean, by the way, I've assumed that this point here is that this line doesn't go under the center of the circle, but over. There are a couple of different cases to this theorem. I don't want to go through all the cases. My purpose is not to give a math lecture in the sense of a class. It's just to give you a feel for how to think about this theorem and how to think about geometrical results in general. So it's a very simple proof and a very simple idea, but it's a very beautiful thing. The only thing that happens is that when you go down here, suddenly the angle changes. Look at that. Here it was an acute angle, and here it's an obtuse angle. So that's sort of strange. What happened? Well, I was sort of upset by this. I didn't like the fact that there was a sudden discontinuity. It troubled me. Now, it turns out it's a very simple fact that this angle down here is the supplement of the original angle. That is, supplement means that the original angle and this angle together, if you add them, make 180 degrees. So this is constant. Well, it's down below, and then it flips right here, and I didn't like that. And so then I noticed something interesting. And I guess I will do something here. I can do a little animation here. And so let's just look at this angle. Now, I guess I can't point at it, but if you look at it, you see that actually when it crosses point B, nothing really changes. You have to look at the proper angle. Let me stop it for a moment, and I don't know how to point things. Now I do need your pointer. I had forgotten that I needed a pointer. I wasn't thinking about that. Unless maybe I can use my cursor on the screen, but that'll be fine. All right, so now, where is it? Do I have to push something in order to? Oh, okay. Can you see that dot? Yes? Okay. So if we look at that part of the this angle here, we can think of this as being sort of this part of the cone. There's a double cone this lower part here and this upper part here. So we can see this as being a part of a cone. And so let's watch this angle as it moves along. I mean, you probably already saw this, but I'm just going to do it anyway. Yeah, it's going the wrong way. All right, so now if we watch it, there it is there, and nothing has changed. It's just we're going along here, and now it's at the top, curiously enough. We just let it come along, and it's coming down, and nothing happens when it crosses. And so, in fact, and now it's become the original angle. That is, it's now the bottom part of the cone again. So we see that in a certain sense, we were looking at the wrong thing. When we crossed here, we changed our attention to that instead of keeping our attention on that. And the reason we didn't keep our attention on that was that those lines weren't there. They were only line segments. And so actually, we should have understood that there was a continuity all the time. But it's sort of like in geometry, there are a lot of little hidden traps like that. You make assumptions about things, and then you find that, in fact, there's a better or a deeper way of looking at it that's more inclusive. And I just wanted to show you that. Okay. I think that's all I need. Now, there's a sort of a flip side to this theorem. Oh, I see. In order to get out of here, I have to go like this. There's a sort of a flip side to this theorem, which is shown here, except that, again, this is too big. I was very careful to construct these so that everything would be visible, and now not everything is visible, and I don't know how to minimize it. But okay. So in this case, what I did was, you see the purple line down at the bottom, just above where it says show caption. That purple line is a line that determines the length of the other purple line, that is the chord in the circle. I can vary that line. I'm not going to vary it right now, but if I shorten it, the one inside the circle will also get shortened. But what I wanted to show you is that if I just keep it at that length, I can go like this. And you can see that the angle measure at the top, where it says measure of angle BAC, it's on your screen, right? Is staying constant. I mean, of course, it's not surprising to you that it stays constant. You might have just assumed that I typed that in and nothing has happened. But it's actually measuring the angle. It's actually measuring the angle, and it is staying constant. In fact, I can show you that. I can show you that I'm not cheating because I'll just change the length of this. And so that changed. And you saw that the angle changed, too. Everything changed. But as you can see, and it goes around and around, and as the chord stays the same length, the angle stays the same. And this is the same theorem, just seen from a different point of view. And I have a little motto, which is related to the title of this talk. The original title was something about Feuerbach's theorem, but that was too complicated, so I changed it. The title was Feuerbach's theorem, a beautiful theorem deserves a beautiful proof. And I don't have an exact title for this lecture, but one of the themes is that a memorable theorem deserves a memorable title. And I'm quite serious about that. I can tell you a little bit about that. But before I do that, I want to give you the title that I found for this theorem. I call it the chord-dangle theorem instead of the chord-angle theorem, because the chord is dangling down there. And so it's a nice way of remembering the name of this theorem. Now, in general, I think it's very important to have names for theorems, because otherwise it'll say in the middle of a proof, it'll say, as we saw in theorem 4.11.12, and then you have to figure out, oh yeah, chapter 4, let me go back and I have to flip through the pages and find theorem 11.12 in chapter 4, and I have to reread it. When in fact, if they had a nice name for it, and if it were memorable, it would be something in a chunk in your memory that you would remember much better and much more efficiently. And so, to me, it's very important to try to give theorems good names. That's a small principle that I like. Okay. Now, I want to let's see. I want to bring up a couple of other small theorems. One that says that the sum of the angles in a quadrangle or a quadrilateral, I'll call it a quadrangle because we're talking about its angles, the sum of all of these angles is 360 degrees. Well, that's not very hard to prove because all I need to do is divide it into two triangles and then I'm done, because this is 180 and this is 180. So we can call that the quadrangle sum theorem, that the sum of the four angles in a quadrangle is 360. Now, the next theorem, ooh, that's not very pretty. The next theorem is if it's a quadrangle that is inscribed in a circle, so 4 points on a circle, let's say like that, then these two sum to 90 and these two sum to 90. I'm sorry, 180, yeah. Yeah. All right, so how do I prove that? Well, again, I put the center of the circle there, and I draw the 4 radii. And so once again, I have some isosceles triangles. So this could be alpha and alpha. I don't know if you can see what I'm writing, but that's alpha and alpha. This we can say is beta and beta, gamma and gamma, and delta and delta. Now, what we know already is that the sum, oh, I'm sorry, I put the wrong, yeah. By the way, let me tell you, I once saw Andrew Wiles give a lecture in Rome. It was about the proof of Fermat's last theorem. It was for a big audience, about more than that, about 30 times this size. I don't know, it was much, much bigger, huge crowd. And in one of his first transparencies, he put the formula for the solution of a quadratic equation. And it was wrong. Some high school kid in the audience pointed it out to him, and he said, "Oh, yes, my secretary must have made a mistake." So I guess my secretary made a mistake in putting that delta there. I don't know. Anyway, all right, so what we know is that the sum of all of this quadrangle is 360. So 2 times alpha plus beta plus gamma plus delta is 360. That's from the previous theorem. And so alpha plus beta plus gamma plus delta is 180. And if we look at that, alpha plus beta plus gamma plus delta, this is alpha plus beta, and that's gamma plus delta. So we're done there again. Or if we wish, this is beta plus gamma, and this is alpha plus delta. So we get it all 4 angles, all 4 little angles there, little angles there. So anyway, quick proof. I like little proofs. I like little results that add up to big things in the long run. Oh, but I forgot, I have to comment on one other thing, which is why is the sum of the angles of a triangle 180? Didn't talk about that. Okay, let's do that also very quickly. So here are the angles in a triangle. So we'll call this angle B, and angle C. Let's just draw a line that's parallel here. The arrows mean the parallel. Okay. Now, if you remember some elementary fact from geometry, it says that this angle and that angle are the same. C is C here. B, this angle here is the same as that one, B. And now we have all 3 of the angles of the triangle here adding up to 180. So that's why that's the case. So now we've shown that thing. One other theorem that I relied on, which I just assumed that you accepted it, which is that if we have a triangle that's isosceles, and by which I mean that 2 of the sides have the same length, then the angles are the same. Now, how do I prove that? I want to give you a proof that actually was found once by a computer back in the 60s. One of the first artificial intelligence programs ever written, and it was a program that was trying to prove theorems in geometry. So I'll draw myself my These lines are the same length. I'll call this A and B and C. Now, the usual way of proving this theorem is to draw the angle bisector or to draw a perpendicular bisector and to do some reasoning, which is fine. It works fine, but there's a shorter proof, which is to recognize that in this figure, actually, I have 6 triangles. I have triangle ABC, I have triangle BAC, I have triangle CBA, triangle CAB, and I don't remember how many I've named, but the one that I didn't name was triangle ACB. I have 2 triangles, one called ABC and one called ACB. Okay? And they turn out to be congruent. Why are they congruent? Because of the rule that says side angle side, SAS. The 2 triangles, in other words, this triangle is congruent to that triangle. You get my point? All right, so if they're congruent, then this angle equals that angle. I'm done. It's a very simple proof, but it's not the kind of proof that's so obvious. This is the kind of thing I told you about geometry having sort of traps in it. It traps you because you think there's only one triangle here and there are really 6. By the way, in case you think I pulled some kind of sleight of hand here, I didn't. I mean, you can easily see that triangle ABC is not congruent to triangle BAC because this angle is different from that angle. So there are 6 triangles here. If you take a random triangle where there's no equality of anything, then there is no congruences at all. But in the case of an isosceles triangle, you do have a congruence of 2 of the 6. And so that's an interesting fact. And it's just a nice way of looking at something that seems extremely simple, and so simple that it tricks you into thinking that it's not what it is. Okay. So let's see. I think I have shown most of what I wanted to do so far. Okay, now I want to prove one more theorem, and then I'm going to go on to something more exciting. Can I pull it? Buttons. Oh, that's too complicated for me. Where are the buttons? What's that?
This one says front, so this one, so they go like that. Okay?
Too complicated.
No.
All right.
Okay.
All right. Sounds good.
And this one, you see, this one just says front, so that one, you can actually make it go back, so now they won't know anything.
Okay.
Okay?
All right. Thank you. Thank you very much. Yeah. All righty. Okay, so this theorem, I'm going to give it a name. I don't actually have a very good name for it. I call it the remote angles pi sum theorem. That's kind of ugly, but anyway, let's see what it says. So we begin with a random triangle. This is supposed to be random. It's not supposed to be isosceles, even if it looks a little bit isosceles. Let's just assume it's just a random triangle. I'll call this A, B, and C. Now what I'm going to do is I'm going to erect 3 triangles, one on each side. So I'll try to draw them in a reasonable way. Let's see. I have not. What I'm doing is I'm trying to make this angle be 60 degrees, and I'm trying to make these not be 60 degrees, and I don't know if I succeeded or not. So let's do, oh, that's not good. 60 degrees, maybe that's about right. Okay? So these are all supposed to be 60 degrees. Oh, no, I don't need, oh, I'm sorry. These are not supposed to be 60. These are supposed to be alpha, beta, and gamma. What am I thinking? So I'll call this alpha. This one is beta, and this one is gamma. I wasn't thinking very carefully. All right. So these sum to pi. Pi is a synonym for 180 degrees. So alpha plus beta plus gamma sum to pi, or 180 degrees, by my stipulation. I'm just saying, supposing that's the case. Obviously, they don't have to, but in this case, I'm making them be that way. All right. Then the theorem states that if I draw the circumcircle for each of these triangles, that is the circle that passes through these points, these 3 points, that's the first one. The next one will pass through these 3 points. And then there's a third one, which will pass through these points. And so let's see how it goes. Something, I have to draw it just right. Oh, that's not quite right. Anyway, the theorem states that this circle will pass through that point. In other words, that all 3 circles will intersect at a single point. That's the theorem. Okay, so how do I prove this theorem? Well, I'm just going to do it very quickly. Basically, I assume that I'm not going to look at this circle yet. I'm just going to look at these 2 circles, the first 2. All right, so they have an intersection point. Pretend that this circle is not here. So this is the intersection point of these 2 circles. And I can draw this line and, this line and this line and this line. All right, they're the lines that join A, B, and C with the intersection point. All right, so here I have what is I have a quadrilateral that's inscribed in a circle. So this angle, let's call it gamma prime, is the complement of this angle. So we have gamma prime inside there, the supplement, 180 minus it. That was what we were talking about in the chord angle theorem. When it flips, it goes to the supplement. Okay, so we have the supplement here. Now here we have beta, and we'll have the supplement here. So this is beta prime, which is 180 minus beta. So what is this angle here? Well, this angle has to be, I don't know if I want to say, I'll say 360 instead of 2 pi. So we have 360 being the total sum of these angles. So this angle, we will have the sum of gamma prime plus beta prime. I will call that alpha prime. And, but gamma prime is 180 minus gamma. Beta prime is 180 minus beta. I really shouldn't have called it alpha prime. I'll call it x, and we will see what it is, plus x. Okay, so, so now we have the 360 cancels this, this, and this, and we can take the gamma plus beta over, and we have x equals gamma plus beta. But gamma plus beta, we stipulated that gamma plus beta was 180 minus alpha. That was our stipulation, that these 3 angles summed to 180. Since we stipulated that, then in fact, x is equal to alpha prime, which is 180 minus alpha. So yeah, okay, so that's fine. So this is 180 minus alpha. So that means that these are supplements, which means that this point is on the circle defined by this thing. That is, all the points on this circle that have the supplement over here lie on this circle. That's the chord angle theorem's converse, which I didn't really prove. But as I say, this is not a lecture in it's not a class lecture. But the idea is that if I have alpha here, then any point on the other side of this chord that makes the supplement angle will lie on the circle of this, on the circumcircle of this triangle. So that basically is the proof. I don't want to go through it in any more detail. The idea was just to give you a sense that if I have three triangles erected that have this property, then these circumcircles intersect in a single point. And we'll now exploit this theorem, this what did I call it? The remote angles pi sum theorem. The remote being this is the far angle in this triangle, this is the far angle, this is the far angle. So they sum to pi or 180, and then they intersect. The circles intersect. It's hard to find a good name often for a theorem because theorems are pretty complicated at times. All right. I need one last theorem, which is quite amusing. And I'm going to do something which is kind of violates my usual religion, which is prove geometric results using geometry. This time I want to prove a geometrical result using a little bit of algebra because it's so cute. It's such an amusing little fact. I hope I can get this to erase. So this theorem is basically the theorem that says the center of gravity of a triangle is the place where the three medians meet. Or put it in, well, yeah, okay, I'll draw up my triangle, my typical triangle here, A, B, and C. And now I'm going to think of A, B, and C as being vectors or complex numbers, whatever you want to call it. And so where is the center of gravity of 3 points in a plane if they are represented as complex numbers or as vectors? Well, you sum them all up, and then you divide by 3. Basically, it's saying it's the average of the three things. Okay? So that's a nice symmetrical expression. So we know that it is certainly totally symmetrical. Now, let me put the midpoint here. This is the midpoint between B and C. Where is that point? Well, that point is B plus C over 2. Okay. Now, supposing that I were going to draw this line, and I wanted to talk about the position of a point along this line. If I wanted the midpoint, it would be A plus this point divided by 2. That would be the midpoint. If I wanted to be a third of the way along, it would be 1/3 of A plus 2/3 of this. Oh, sorry, yeah, if I'm saying it correctly, I average 1/3 of this plus 2/3 of this. If I want it to be a third of the way, 2/3 of the way down, that is, not as much weight to A, twice as much weight to this point. It's like I'm adjusting the weights. If I want it to be closer to A, I can say 90% A, 10% of this point. But I'm going to go 2/3 of the way down, which is 1/3 of A and 2/3 of this thing. So 1/3 of A plus 2/3 of this thing. All right, so I've gone 2/3 of the way down this line. All right, now the 2's cancel. And look, I have 1/3 of A and 1/3 of B and 1/3 of C. And that's that symmetrical expression. That's the center of gravity that I just wrote at the beginning. And so this very simple expression, which seems to be totally asymmetrical at first, turns out to be symmetrical. And that means that it doesn't matter whether I did it with A and the point over the midpoint of this side, or with B and the midpoint of that side, or C with the midpoint of that side. They all hit each other at that point. So that's the centroid theorem. Centroid being that point. All right. Now, I'm going to go through another theorem. This is a complicated theorem, and it's attributed to Napoleon. And Napoleon was very interested in geometry. And in a book that I read, it says that Napoleon was probably not good enough at geometry to have found this theorem. I think that's probably, well, I doubt that. I think that he might very well have been, he may not have found the proof, but I don't see why he couldn't have found the theorem, or at least the first part of it. And I'm going to show this theorem actually the way I think of it. I mean, different people have a different way of talking about it. I divide this theorem into 4 parts, and I'm going to show you all 4 parts. Now, I stated earlier that a memorable theorem deserves a memorable title. I think a memorable theorem also deserves a sonnet. And so I'm going to give you a sonnet about the Napoleon Theorem. And then what I'm going to do is I'm going to give you the full sonnet. I'll read it to you. You won't know what I'm talking about probably, unless you know the theorem already. That's fine. Then I will go through the sonnet line by line, 1 picture per line, 14 pictures, and that'll give you the whole thing. And then I'll read you the sonnet again. So here we go. Can you see it on the screen? No. How do I make this bigger? Oh, now it works. Very good. Okay, I'm not going to complain. I mean, I want to complain since it didn't before, but oh, I know. This is a different program. That's what it is. We're now in Word instead of being in Geometry Sketchpad. Okay, all right. Can you see it now? What's that? If I move it to like that? Or did you mean like that? Is that good? All right. So I'll read it out loud. Equilateral triangles 3 will erect, facing out on the sides of our friend ABC. We'll link up their centers, and when we inspect these segments, we find tripartite symmetry. Equilateral triangles 3 will next draw, facing in on the sides of our friend BCA. Their centers will link up, and what we just saw will enchant us again in its own smaller way. Napoleon triangles, too, we've now found, their centers seem close, and indeed that's the case. They occupy one and the same centroid place. Our triangle pair forms a figure in ground, defining a 6-edged torus we see, whose area is the same as our friend CAB. All right, so let's see. Okay, so let's go through this one line at a time. Oh, I may have to change the view here. Single page, that's correct. Oh, I see. It wants me to get it smaller. It doesn't like it to be big. Okay. All right, I'll read the lines aloud if you can't read them yourself. Equilateral triangles 3 will erect. So my triangle ABC is the dark one, and those are the 3 that we've erected. By the way, you'll notice that this is related to the picture I drew over there. It's a special case where, in fact, instead of it being alpha, beta, and gamma, it's 60, 60, 60 on the outside. That's why I got confused at the beginning, because I was confusing it with this theorem. All right, so equilateral triangles 3 will erect, facing out on the sides of our friend ABC. ABC is supposed to be a random triangle here. It looks like a right triangle a little bit, but it's actually not a perfect right triangle. Anyway, it's supposed to be a random triangle. So there they are. And we'll link up their centers. So there I've indicated the centers of each of them, and I put dotted lines joining their centers. We'll link up their centers, and when we inspect these segments, we find tripartite symmetry. In other words, I don't know if you can see it on your screen, but I put the little line that crosses it to indicate that all 3 of them have the same length. Can you see that? Yeah, they are all the same length. This is an equilateral triangle itself, despite the fact that ABC was a random triangle. This will be an equilateral triangle. All right, next, that's for part 1 of the Napoleon sonnet. Part 2, equilateral triangles 3 will next draw, and you can see what I've done is I've drawn them now, instead of facing outwards, I've drawn them facing inwards. In other words, I've flipped the equilateral triangles that I originally drew inwards. Okay, equilateral triangles 3 will next draw facing in on the sides of our friend BCA. And I only changed the order of the letters there so it would rhyme. It's still the same triangle. All right, so there they are. Their centers will link up. All right, and what we just saw will enchant us again in its own smaller way. Another equilateral triangle. I'm not sure Napoleon would have thought of this one because, once again, this is one of those typical cases where, you know, you don't think of the flip. You think of the outer one, that seems natural. The inner one seems kind of weird because they cross each other. Nonetheless, it's just as reasonable. So there there's another subtle thing here, which is that if I go back a moment, I'll go back to this picture. If I, as you see, I labeled, well, you may not be able to see, but the top vertex of my triangle is A, then the lower two vertices, as in these pictures. This is always A, this is B, this is C. Now, when I take the midpoints of these three triangles, and this one, the lower one, the one on the bottom is called A sub n. The one on the upper right is B sub n because it faces the vertex B. And the one on the upper left is called C sub n because it faces the vertex C. So if you go around A sub n, B sub n, C sub n, you will find yourself going in a counterclockwise direction. In other words, where's that pointer? Just to make sure you know what I'm talking about. ABC is counterclockwise, because if I go from A to B to C, I go in that direction. And here is A sub n, here is B sub n, and C sub n. And if I go around, I will be going around in the same direction. Both of them are counterclockwise. However, if I do the inner one, it turns out, I'm not going to prove this or anything, but it turns out this one goes in a clockwise direction. In other words, the one that corresponds to side BC is there. So the center of that triangle is there, that one. That's the one that corresponds to A, and so forth. And if you trace them out, you'll find that you're going not in a counterclockwise direction, but in a clockwise direction. So this triangle is sort of rotating in the other direction. The outer Napoleon triangle goes in the same direction as ABC. The inner Napoleon triangle goes in the opposite direction. That's a kind of a small theorem, but it's an interesting fact. Napoleon triangles, too, we've now found. Their centers seem close, and indeed that's the case. I tried to show you their centers here by drawing some dotted lines. They occupy one and the same centroid place. Now, what do I mean by that? I mean, though the centers of those two triangles coincide, and they coincide in the centroid of triangle ABC. That's the center of gravity. That point is the center of gravity of triangle ABC, and it's the center of both of the Napoleon triangles. So that's another lovely fact, another Napoleon theorem fact. That's part 3. And the fourth part, our triangle pair forms a figure in ground. That is, well, you can see what I mean, basically. Defining a 6-edged torus, we see. And so here we have a funny kind of a donut. And we can talk about its area, whose area is the same as our friend CAB. I just changed the order for the fun of it. So, in fact, you can think of this, the area of the torus, if you wish to call it a torus, as being the sum of the areas of the two Napoleon triangles, where one of the areas is considered to be negative because it's going in the wrong direction. So you add, another subtle thing of geometry, you don't think of triangles as having a directionality normally. But if you really think carefully, triangles do have a directionality. That is, if you label their points and you have a way of mapping one to another, that you may find sometimes they go clockwise, sometimes they go counterclockwise. And so in this case, we have a clockwise one and a counterclockwise one. And if we take the area of one and call it positive, then the area of the other one will be negative. So we're actually adding their areas in some sense. We add their areas together or we subtract them, however you want to phrase it. But that difference is the same as the area of the original triangle. Now, I'm not going to prove all of that to you. But I just wanted you to understand. In fact, the proof of the first part of Napoleon's theorem is just a special case of this, essentially. We'll see that in a moment. And I'll go back, just finish up, just so that you can see the sonnet one more time. Equilateral triangles 3 will erect facing out on the sides of our friend ABC. We'll link up their centers, and when we inspect these segments, we find tripartite symmetry. Equilateral triangles 3 will next draw facing in on the sides of our friend BCA. Their centers will link up, and what we just saw will enchant us again in its own smaller way. Napoleon triangles 2, we've now found. Their centers seem close, and indeed that's the case. They occupy one and the same centroid place. Our triangle pair forms a figure in ground, defining a six-edged torus we see, whose area is the same as our friend CAB. So those are the 4 parts of the Napoleon theorem. Now I want to show it to you in another way. So here, oops. This should work. All right. Firstly, let me just show you. There's the centroid of triangle ABC, and if you want, I can show you how it works when I move this around. Okay? Now, those are the 3 equilateral triangles. On my screen, they're not equilateral. My screen has been affinely distorted. But in your case, it's okay? Okay, good, good, good. All right, so there are the triangles. Now I will show the equilateral triangle that they form. There it is. And now I'm going to draw the circumcircles that I have in this theorem. And we'll start to come in for a landing on the proof of this theorem. So what I drew there is those 3 lines that I already drew here, but in the special case where these are all 60, 60, 60. So these are 180, 180, 120, 120, 120. And that's actually a very interesting point, that point in the middle of the triangle that I've labeled F. I labeled it F for Fermat because this is called the Fermat point of a triangle. And it's a beautiful point. It's actually also called the first isodynamic point. Fancy name, but it basically means those 3 angles are equal. It's poised beautifully. It's, instead of being the center of gravity, and it's certainly not the center of gravity, you see G. Let's move it around a little bit just so you can see that they are completely independent of each other. Okay, so there's the Fermat point and the G, the center of gravity, being quite independent of each other. But that Fermat point corresponds here to the place where the 3 circumcircles meet. Okay, so we know that those 3 circumcircles meet because of our previous theorem, because 60 plus 60 plus 60 adds up to 180. So it's a special case of this theorem. So these 3 circles all meet in a point. So we draw these lines, and they are at 120. They make 120-degree angles. Well, now let me point out a quadrilateral that we have on the screen here. Let's look at this quadrilateral here. Dun, 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 dun. Okay, there is a quadrilateral. This connection here is connecting the centers of 2 circles, this circle and that circle. And so this is a chord that belongs to both circles. So this line has to be perpendicular to that line. This has to be a right angle. Similarly, this, we have a right angle right there. Do you see what I'm doing? The black line and this dotted line, they have to cross because this is a chord of this circumcircle and also of that circumcircle, and this is connecting their two centers. So this is 90 degrees. There are 90-degree angles here, 90-degree angles here, and 90-degree angles here. So this is 90, this is 90, and here we have a quadrangle. These two sum up to 90, so sum up to 180. So these two have to sum up to 180 because the total has to be 360. So that means this was 120, that has to be 60, and similarly this has to be 60 and this has to be 60. So we have a triangle, all of whose angles are 60. So that means it's equilateral, and that's the proof. It's based on this more general thing, and this is a special case. All right, so I'm only going to prove that part, one of the four parts of the Fermat, of the Napoleon theorem, but I wanted to at least give you a flavor for how it can be proven. Okay, now let's hide these one by one, and let's look at the other side. All right, we'll do the inner Napoleon. There are the flip equilateral triangles. We show the segments. There's the little Napoleon thing. Now we draw the circumcircles. Now they are overlapping. And there's the second isodynamic point. I drew full lines this time instead of line segments because the second isodynamic point is one. The first I could have drawn for full lines. Then instead of it being 120s, you would see 60-degree angles. It's just more, it looks prettier inside where you see the 120s. So really the isodynamic points are defined as where they all meet in 60-degree. These lines meet in 60-degree angles. So this is the second isodynamic point. So there are two of them. And once again, this is a surprise because you initially think that a point, you think of it in terms of 120-degree angles, and you don't think of this. This is another of those cases where your default assumptions sort of lead you astray. If you replace segments by full lines, you get this, and you realize that you left out half the picture. Two isodynamic points, not just one. And then finally, just showing the measurements. There are the measurements of the areas, and if I move this point around, you'll see that the areas of the two triangles at the bottom of this set of measurements, here it says 46.51 centimeters squared, they stay exactly equal. So here we have this thing. Now, I think what I wanted to do is I want to move on to a question that I asked myself many years ago, which is, I'll hide this as well. Start again. I asked myself just a simple question: can I ascribe an equilateral triangle around ABC? Meaning, can I make an equilateral triangle such that its three sides pass through the points A, B, and C? Now, that may not be obvious that I can always do so, but let me show you one. There we are. Oh, it's too big. Well, I'll reduce this. I'll reduce point A a little. Oops, come on. There we go. Now you can see it. And indeed, I can make, no matter where I make a move, I can make an equilateral triangle that passes through the vertices A, B, and C. So that's a pleasing fact. However, it's not a unique fact, as it turns out. Look at that. I can get a whole bunch of them. Now, this is a subtle thing. Well, I guess I'll just leave it there. You can get the idea, even if it goes off the screen a little bit. But you see that, you see I can always do it no matter what angle I wish it to be at. I can tilt it and it'll still, but it changes size. Okay, so let's let's look at this and let's let it go all the way around. Look, something interesting happens. It turns out, once again, our default assumption that it has to involve line segments is wrong. It's really the full lines that are involved. You can see that on my equilateral triangle's sides, they do pass, the sides of my equilateral triangle pass through A, B, and C, but only in the sense of lines, not line segments. The default assumption is to think that it's outside of the triangle, but in fact, sometimes it can be totally inside the triangle and it's still ascribed. You know, ascribed means drawn outside of. The Latin prefix ex is there. It means it's outside of it. And so your assumption is to ascribe a triangle around another triangle makes it sound bigger, but it can be smaller and it can be inside. Again, violating your assumptions. Very interesting. So this is a triangle ascribed around ABC. And if I move it, if I take the controlling point and move it around, I can see that it will sometimes be inside. And what is it at that? What is it right there? It's the Fermat point. It's where those lines meet at 60-degree angles. That's the Fermat point. That's the littlest one possible. There's also a biggest one. There's a biggest one. Okay. And let me show you something interesting. Those are those circles that I had before. Let's look at this. Let's watch this. Look at where those points of the triangles, that this equilateral triangle ascribed around ABC, all of its vertices lie on those circumcircles, which were created for the Napoleon picture. When you think about it, it's not such a big surprise, but there we are. There it is. So it's actually quite a beautiful construction. And where is the biggest one? It's when the line passing through A, well, I can get over here. It's when this line here is perpendicular to that line. That's the biggest one, where that line is perpendicular to this line, where that line is perpendicular to that line. Okay. So that's the Fermat point right there, and as you will see, the smallest one coincides with it. Whoop, boing. All right. Very nice. Now, turns out, once again, I fooled you in a certain sense. You probably assumed, maybe not all of you, but probably all of you assumed that there is only one way of ascribing an equilateral triangle around a given triangle. No, there are two ways. This is what I would call, there's a clockwise way and a counterclockwise way. This is the counterclockwise way. There's a clockwise way as well, and let's look at that. I'm calling it the anti-ascribed one. So let me get rid of this one just for the moment. You can see the difference. I'll also get rid of these circles. All right, let's just watch this one. You can see that it's an equilateral triangle, and you can see that just as before, it's ascribed in the sense that its three sides pass through A, B, and C. So it's a complementary one, and it has, guess where that point is? Second isodynamic, exactly. So there we go. We have very nice symmetry. We have two ascribed equilateral triangles. All right, I will show both of them, and let's look at them as they go around. There they are. Okay, and I think that I'm going to wind up with one more sonnet, and so let's go. This is a sonnet that I wrote about this result. I think I've given you the full result, although maybe not, maybe not. All right. So the sonnet will reveal that there's a little bit more to the picture. Yes. Can you read it, or do you want me to make it bigger? Bigger? I'll make it a little bigger. Okay, I'll even make it bigger, and then later I'll reduce it. Within ABC, oh, I forgot something. I'm sorry, I have to go back for one moment. I forgot that I wanted to show you this also. Because when you can ascribe a triangle, you can also inscribe a triangle. So I want to show you what happens if you inscribe an equilateral triangle inside a triangle. Okay, so can we always do that? Yes, there we can. There's an inscribed one. An inscribed makes you think that it's smaller, right? And of course, that's going to be violated. That assumption is going to be violated. Let's watch it as it moves around. It's staying inside pretty nicely, but oops, it went outside onto the 3 dotted lines. So it's still inscribed. Oh my gosh, it's getting bigger and bigger. It's covering the whole screen. And now it's coming back. It went out to infinity, by the way. It made it very quick. It went faster than the speed of light. And it came back. And it came back. But I go around the circle, and at some point it goes out to infinity. It visited the Andromeda galaxy, but very briefly. And it came back. So those are the inscribed equilateral triangles. But of course, there are 2 of them. There's the other one. One of them is clockwise, one of them is counterclockwise. So there they are. 2 different ones. Okay, so we have some fun there. Yes, one last thing I need to do. Before, I want to go back to the preceding thing because I forgot one other thing that's beautiful here. And I wanted to show it to you. All right, so I have to do that. You see that point there? What point is that? In the very middle? That's the middle of the ascribed equilateral triangle. That's the center of the ascribed equilateral. I want to know where that point, what that point does as I trace through all of the possible ones. So I will trace it. Okay, now let's see what happens as this goes around. It's drawing a circle. Look at that. So we get a circle. Now the question is, what circle is that? What circle is that? It's an interesting question because, well, it turns out to be centered on a point that we already know. It's centered on the centroid of ABC. And moreover, and this is something I guess I can show you very briefly. Let's look at the inner Napoleon thing and the inner Napoleon triangle. There is the inner Napoleon triangle. Look at the 3 points. Is my cursor showing up for you? So those 3 points are on that circle. So let's watch this as we move around. You see the point is moving around the circle, and every once in a while it goes through the 3 points of the equilateral Napoleon triangle, the inner one. And similarly, I'm not going to show you right now, if I were to take the other ascribed, anti-ascribed equilateral triangle, its centers also will form a circle centered on G, and it will be the outer Napoleon. So it's rather complex, rather elegant results. Okay, now I come back to my sonnet. Okay, within ABC, here's a triangle drawn, and I said within, meaning now I'm talking about inscribed. That's why this reminded me I had to cover the inscribed case and the ascribed case. Within ABC, here's a triangle drawn, and we'll do it line by line. Can we get all 3 sides to be equally long? The answer is yes. And then slowly will dawn on our curious minds that in fact there's a throng, meaning infinitely many of them, with some large and some small. There's a smallest, in fact. But how is it poised with respect to its frame? Now let's shift to the outside. Our question's the same. Is there one whose 3 sides are alike and exact? Now we're talking about ascribed equilateral triangles. Again, there's a throng of them. What do we find but that now there's a largest? And this one's aligned edge by edge with the smallest one sitting inside. You'll see what I mean in a moment. Thus, parallel partners we've found, groom and bride. But let's not forget ABC, wedged between. Its area, behold, is their geometric mean. All right, let's look at this now bit by bit. I've got to reduce it to make this program happy. Come on. Maybe it needs it to be smaller yet. Okay. Smaller yet? No. I don't know. I don't understand this. Maybe the view is wrong. Single page. Okay. All right. There's the sonnet. There's the first line. Within ABC, here's a triangle drawn, a random one. Can we get all three sides to be equally long, step by step? First, I make it isosceles, and then I'm going to adjust that bottom point or I'm going to adjust things so that I get it to be equilateral. The answer is yes. And then slowly will dawn on our curious minds that, in fact, there's a throng, an infinite number of them. With some large and some small, there's a smallest, in fact. And there I've drawn the smallest one for you in red. What? What? The projector. But can you see the picture? But just not the colors? Not the colors, or what? Good. Great. Okay, I'm glad we salvaged that. Weird. All right, so here we are. There's a throng, and here's the smallest one, and it's red. Okay, but how is it poised with respect to its frame? This is a sort of awkwardly phrased question, but, you know, I was writing a sonnet. So, in other words, what angle does it make? You know, something like that. Now let's shift to the outside. Our question's the same. Is there one whose three sides are alike and exact? And there is one. Again, there's a throng of them. What do we find? But now there's a largest. And this one's aligned edge by edge with the smallest one sitting inside. In other words, they're parallel. The smallest inscribed is parallel to the largest ascribed. Thus, parallel partners we found, groom and bride. But let's not forget ABC, wedged between. Its area, behold, is their geometric mean. So I've symbolized that by multiply the areas of the two equilateral triangles and take the square root, and you get the area of the original triangle. So that pretty much covers what I wanted to do in this lecture. I think, do I have any final words? Yeah. I guess I just wanted to say this is the beauty of geometry, and it gives you a feeling for why I fell in love with it, and I hope to have made you at least a little bit infatuated with it. Thank you.